paper, we present a model that learns to reconstruct deformable 3D objects from monocular videos. After training, the model is able to predict articulated 3D shape, pose, as well as texture from a single image, which allows for animation and novel view rendering. Our model is trained using monocular videos of an object category, such as birds. We obtain object masks and optical flow from off-the-shelf models and use them as supervisory signals during training. In particular, unlike existing methods, our model does not rely on any explicit 3D, keypoint, or viewpoint supervision, nor does it require a 3D shape template. To do this, we propose a photogeometric autoencoding framework, where the model learns to decompose an input image into shape, pose, and texture, with the objective of reconstructing the input image through a differentiable renderer. In addition to the image reconstruction loss, we also compare the rendered masks and optical flow to the automatically obtained pseudo-ground truth and minimize their difference. We represent the shape of the bird in each frame using an articulated shape model. Specifically, given each frame, we first predict a category-specific prior shape by deforming a sphere. This prior shape is shared across all birds and is directly optimized as trainable parameters during training. We then predict an instance-specific shape for each bird at rest pose by deforming the prior shape. So far, both the prior shape and the instance shape are enforced to be bilaterally symmetric. This instance shape is then articulated for each frame with a skinning model by predicting the transformations of a set of virtual bones. We then transform the articulated shape with the rigid pose, render it with the predicted texture, and minimize the reconstruction losses for training. Here are some results obtained using our model. Learning from videos allows the model to produce a 3D shape that is consistent not only from the input view, but also from any other novel viewpoints. Our model also recovers full texture of the objects by enforcing symmetry. We compare our method to 4 other methods. Without additional geometric supervision such as keypoint, viewpoint, or template shapes, all the existing methods fail to learn correct poses and therefore are not able to produce sensible shape reconstructions. In particular, here we show the reconstructed shapes of 2 frames in a sequence. Our model is able to produce consistent shape reconstructions, whereas all other methods fail. Here are some more examples. We analyze the learned shape space using principal component analysis. Our model learns shape deformations for different bird instances. It also learns various articulations through the bone-based scanning model, including typical head and tail movements. We can also transfer the texture from one bird to another by simply swapping their texture predictions. Our model is indeed able to learn meaningful correspondences between different instances. With the resulting skinning model, it is easy to animate a mesh simply by adjusting the bones. Here are some examples.